Greetings. Welcome to Systemic Societal Health, the podcast that explores how the science of energy networks creates a logical, practical, rigorous, and heartwarming understanding of what goes into building healthy human networks. I'm your host, Dr. Sally Gerner, Research Director for Edinburgh University's Planetary Health Lab. Today we'll be talking with Dr. Anamaria Berea about how energy network science fits into economics, period. With PhDs in economics and computational social sciences, Dr. Berea is an associate professor of data sciences at George Mason University in Virginia, a research scholar in astrobiology for Blue Marble Space Institute, affiliated faculty with NASA Frontier Development Lab, and a research affiliate for the SETI Institute. Welcome, Dr. Berea. Okay, so what I want to talk about today is kind of like why my work connects with your work.
Okay.
And particularly you have a background in economics as well as complexity, right?
Yes.
Particularly, my understanding is my kind of energy flow stuff works very well with some set of early economists who did flow network kinds of things.
Mm-hmm.
I mean, certainly things like Keynesian economics is very much, it's of the same basic idea. I don't know if they explained it the same way, but
Yes, the original Keynesianism was to some degree, yes, it was related to the idea of flows, but I think the original Keynesian economics was actually much more static than what we understand through flows right now, because it was all about equilibrium at the macro level and achieving equilibrium at the macro level. Yeah.
That's interesting. And the equilibrium that they were trying to achieve was, of course, not really a thermodynamic one, more as a homostatic.
That's right. And especially when it comes to macroeconomics and, very, very large scale economies, the whole goal was to achieve some equilibrium between the labor market, the financial markets, the goods markets, right? So, yeah.
Well, so that's interesting. But they ended up finding a rationale for why there had to be more money put into the demand side of things rather than just the supply side, right? So you had to pay workers stuff. They had to have jobs.
Right. So that was more on how do you adjust for the economic imbalances and how do you have the government interfere and adjust for these economic imbalances, which now we know that, that's how complex systems are, right? They are in continuous evolution and economies are in continuous evolution. But at that point, because they were using mathematics a lot and also the views from physics, where again they were looking at more static systems. The goal was to achieve equilibrium without perturbations, without any any of the characteristics that we now know that social systems, economic systems have.
So, I mean, of course, part of the evolutionary process is punctuated in an energy flow point of view. And so it sort of oscillates between relative stability, a relative homeostatic thing, which you need in order to get anything done, and these periodic places where you sort of have to break out, you have to learn.
That's right. Yeah.
Because what you're doing is not sufficient for whatever stage of development you're at, or whatever shortfalls or errors or inconsistencies or corruptions.
Yeah, that's right. This kind of pattern that is called kind of like a staircase evolution. Where exactly you have periods of perceived stability, then you have like a jump or a push, that jolts the system, and then another perceived stability. But it's also it's all part of the larger evolution of the system. So this kind of staircase type of growth and evolution has been observed in companies too. So at the micro level, in firms.
Right. Yes. I mean, I've actually. Well, can you say somebody who does that kind of evolution in business systems?
Well, I know it has been studied a lot when it comes to startups and successful startups and what constitutes, a successful company. How do you build a successful company at the microeconomic level in entrepreneurship studies? So they did study this a lot, and they did observe that. For example, when it comes to growth in employment, when the companies need to hire, they usually go through these periods of massive hires, and then stability, and then another period of hiring, and then stability. And it's the same when it comes to financial revenue. They go through a period of more income and financial revenue, and then less. And particularly if we are talking about younger companies, more successful startups, once they become fairly big, they start to level out more. So they don't have as much of the staircase kind of growth any longer. And I know this has been studied in the how was the name of that project? It was the Startup Genome project was studied by Stanford and Berkeley by university team.
Interesting.
Yeah.
So one of the driving force for me from a flow network point of view is always this built up pressure. So unmet human needs or underutilized human resources create pressure, which eventually drives the system to either learn a better way, enter a new stage or new pattern of organization, or it basically disintegrates or blows up because it can't adequately handle the pressure in the current context.
Right.
Now, people who are studying this in economics or in business, do they look at those kinds of things? Do they look in terms of pressure or?
I don't think they look. Well, when it comes to pressure, one area in macroeconomics again has been also in neo-Keynesianism and some of the macroeconomic policies about exogenous shocks. That's what they are called. So, for example, when something unexpected happens, like a pandemic, right?
Yeah.
Or like war, or something that does not have anything to do with the inner workings of the economy. They are called exogenous shocks, and they are parameterizing this into these macroeconomic equations. So I know it has been studied from the economic policy point of view at the macroeconomic level. In microeconomics, I am not that. I honestly don't know. I'm not that familiar with that.
See, it's interesting because for me, it's not necessarily exogenous shocks that are the problem. It's frequently the endogenous problems, basically the increasing fragility of the overall infrastructure, such that it's no longer able to rebound, be resilient. It can't rebound from one of those exogenous shocks.
That's right. I mean, if we are looking at Earth as one planet on itself, it basically has, it has only endogenous effects, right?
Right. Yeah. Right.
Only endogenous processes. Now it depends on how we look at these. If we want to separate, let's say, the economy from the environment, then if something happens in the environment, although we know that they co-evolve, right, and they influence each other, but for modeling purposes and to understand how these work, obviously the researchers are separating them. So not knowing what causes something in the environment, they just observe that effect, and then they observe that impact into the economy, for example. And that's what they call exogenous shock. So they don't have to worry about where that thing comes. It's just how it's going to affect the current system or the current model. So yeah.
That's interesting. So they don't really look at the endogenous problems.
No, not until complex systems thinking, right? It's just that now here's the thing that if we want to model everything, we cannot, right?
Right.
We really can't model everything. So we do have at some point to make some delimitations, may put some boundaries on what exactly is our system and what's outside of our system, even if they do influence each other. And there is maybe, like in chaos theory, there is the butterfly effect from one system to another. But if we wouldn't be able to model or study them if we had to take into account everything. So that's one of the limitations for how we are looking at this. But yeah, there are definitely systems that co-evolve more tightly with each other versus systems that are, more separate from each other.
So this is really interesting because, of course, it brings up, so the difference between complexity theory and chaos theory, by which I mean the geometry of behavior, which is these universal patterns that are essentially, it's almost like it doesn't matter where you draw the boundary of the system under study, because you don't have to study the movement of everything. You don't have to model it per se. You just have to look at how well it approximates some optimal universal pattern.
That's right.
So so that actually this explains actually a lot, because and I guess studying the geometry of behavior is what they called it when I was in grad school for nonlinear dynamics. And the joke was from this guy, Stanislaw Ulam. He said,
"Oh, he's a science fiction writer, right?"
Is he? I don't know.
Or maybe I'm
Maybe
confusing
so.
him. Maybe I'm confusing him with someone
But
else.
anyway, he said that calling nonlinear dynamics, calling chaos theory nonlinear dynamics was like calling zoology the study of non-elephant animals.
Yeah. Yeah.
Which takes a while to wrap your mind around it, but it basically says most systems fall into this geometric approach.
Yeah. It's actually, sorry, I was thinking about Stanislav Lem, who is the science fiction author.
Oh, okay.
Sorry. Yeah. Yeah, no, I mean, I agree that most, I guess, well, not just living systems, but whether to or complex systems, right? Some of them are chaotic, but not all of them, right?
Well, I'm not talking about chaos per se.
Right.
I'm talking about the natural geometries of the vast majority of systems, the ones that are okay. So in this view, you sort of divide all possible systems up into three main groups. There's the simple systems, which is what classical systems are built around, where there's one incredibly dominant effect. In fact, that effect is it's like huge sun, itty bitty planet. So the gravitational of the sun pretty much completely determines exactly where this particular planet's going to be.
Yeah.
And it's wonderful for the systems it works on, but most systems are not like that.
Right.
So the opposite end was the systems that are very mutually, well, they're weakly coupled and very about the same size. So you have randomly colliding molecules. They're all pretty much the same size, and so you get statistics, which are disordered complexity. And then the mean in the middle ground is this ordered complexity, where there's not a single thing, and there's not completely, but these things are coupled tightly enough that there are multiple causes, but that they also mutually affect themselves in a way that produces this naturally occurring order. And then, of course, so in theory, this nonlinear dynamics is really the study of that naturally occurring order of relatively mediumly coupled bodies in space, or
right. But also nonlinear dynamics. I mean, from what I know, the term comes from the fact that these are systems that we cannot predict or model using linear equations, right?
Right.
So nonlinear dynamics comes from the idea that there is cause and effect, but it's very difficult to find the cause because we cannot easily predict that.
Right. Okay. So here's the, okay. So let's do the real funky stuff, which is, so you go back to the Aristotelian notions of causality, of which there are four. So there's efficient causality, which is the immediate, the arrow struck the guy and killed him, so that's
right,
the efficient cause. And then, but then there's this formal cause, which is kind of like if you're building a house, then there's this blueprint for it.
Mm-hmm.
So it's basically the overall shape that it's taking on, the overall pattern of behavior. And there's this, when I was in grad school, there was a guy named Pedro Chutanovic, I guess it was. Anyway, he had a book called Universality Theory, which is all about how if you took all of the possible types of equations, they boil down into only about, like, I think at the time there was like 150, 120 different overall major patterns of behavior.
Mm-hmm.
And that, so you could get a pretty good approximation of what that system was going to behave like from the smallest and simplest member of that class, universality class.
Mm-hmm.
So I guess the idea was that, and then in the end you have final causality, which is what purpose is this serving? And from a what was the fourth one? Efficient, formal, final, and something or other. Oh well, my memory is gone. But anyway, but
I can look it up. Aristotelian causality. Yeah.
But so the geometry of behavior is really about those formal causations.
Yeah.
And the idea. Go ahead.
So I found it. So there is the material cause, that out of which, like the bronze of a statue,
right?
The formal cause, which is the form, the shape of a statue. The efficient cause, or the primary source of the change or rest, which is, for example, the father of the child. And the final cause, the end for the sake of which a thing is done. For example, health is the end of walking, losing weight, purging drugs, and surgical tools.
Right.
So yeah.
But so when I was doing this kind of stuff, I mean, classical science is primarily involved in efficient causality.
That's right. Mm-hmm.
And maybe material causality, but particularly the efficient causality. And it only works on really simple systems where there's one overwhelmingly main cause.
Mm-hmm.
It's the formal thing. So the hope of the nonlinear dynamics is that you can do certain types. You can do geometric prediction. You can't predict exactly the moment of change or even the internal cause of change. What you can predict are things like, change will occur if the pressure is building.
Yeah.
Change will occur if the system is becoming brittle.
So basically, we can predict that. We can largely predict the change of the system, but we cannot predict how the system will change.
Exactly, which actually makes sense. Well, you can predict some aspects of how it's going to change.
How it's going to change, but not, not, Well, yeah, because, usually for the purposes of applying science to our everyday lives, we are taking this engineering approach where we need to know exactly if you alter the state of A, how is that going to reflect in B, right?
Right.
So yeah.
So we're in this kind of view. So if you're applying all of this stuff to human systems, the two big things are how your culture is set up, and the culture is dependent upon having a common cause basis, so that you are working. So everybody's working in a way that is mutually beneficial at some core level. So, and the other part of it is that you're designed such that you both harness this kind of ecology of knowledge with lots of different skills and insights and ideas, and all coming together towards building a better society.
Yeah.
And you have it, and it's oriented towards ongoing learning, so that you continually re-examine your ideas.
Yeah, which is again like a better approach to science than we have right now, where like even in data science, right, that I work with every day, we are only looking for specific and exact causes in the immediate causes in the data, but it's all the contextual factors are basically removed because they are not captured in the data.
Right. Now, in this case, you would have contextual factors, but they would be things like pressure. But then a lot of the factors would also be endogenous, because they would be things like fragility.
Yeah.
Or necrosis, which is kind of a variation on fragility.
Right. So because the system changes both internally and it has effects externally, right? So and those external effects can, again, through feedback, change the system again. And it's I'm thinking that these can or cannot be independent factors, right? The internal change and the external change that are affecting the system.
Right. Yeah. Because and in fact, there's all these modeling problems, which is where you divide up the external ones from the internal ones. And that's absolutely necessary for certain types of explorations. It's just that it doesn't necessarily, it's orientate. Actually, I shouldn't say that. So if you're modeling this thing and worried about exogenous factors, what's the goal in mind here? What are you trying to accomplish by?
Yeah. So I guess the idea is how, when it comes to economics, you have to think about policy, right? And what kind of policies can you design that will affect the economy? So those are the exogenous factors. And you are thinking about, okay, what can I do in this big area, let's say like industry or like labor market, through which I can change the system, right? And is it because I infuse more money in the economy? Is it because I lower the general interest rate? Yeah.
So, I mean, and I get how obviously things like changing the interest rate have clear effects, but it also depends a lot on A, what's happening internally, and B, what's happening externally. So like we're in a situation now where lowering their interest rate doesn't make any difference.
That's very true. On another hand, in economics, we also talk about this thing called unintended consequences.
Yes.
Right, because while you can foresee some immediate changes, you cannot foresee others. And the greatest example is the one with about minimum wage, right? Because it has been shown that setting a higher minimum wage actually increases unemployment instead of reducing it. So it has quite the opposite effect. Because again, there are all these unintended consequences that you cannot think about, or maybe so you can understand them maybe from historical cases or examples, or if you have a lot of data that maybe it doesn't seem that it would be connected with each other or correlated with each other, let's say two completely independent variables that might have an effect on with each other For example, if we are talking about the minimum wage, let's say that another variable would be about childcare, right? So you wouldn't think that there is an immediate connection between the minimum wage and childcare, but looking at the data, you might find that connection. So it's definitely when we cannot predict, and it's really hard in complex systems to predict everything. Just like you said, you can predict the general change or how the system is going to change in general, but there might be some effects that are unpredictable, and only after you observe them and you try to understand them, then you can readjust the original policies and try again. While we don't have enough room for trial and error, because trial and error is expensive, right? It's expensive both in nature and in human societies. The best way to do that is looking in history or through the data, if that's possible.
Well, this is interesting. First of all, I completely agree that what you have to do is basically try something out and then re-examine it, and because that's basically a learning process from my point of view.
Right. Mm-hmm.
But okay, so as a minor non sequitur, Brian Fath has this adaptive cycle, which is basically at different points in the system's lifespan, the context changes, co-evolves with the system,
Mm-hmm.
or big enough systems anyway. And as a result, things that work or produce one effect at one place in the cycle produce a different effect at different places in the cycle.
Mm-hmm. Mm-hmm.
Which is sort of, it's part of it is a readiness kind of
Mm-hmm.
thing.
Mm-hmm. Yeah.
So, in our case, it's ideas like we're talking about now would have, they would have gone nowhere before there were computers, for instance.
Mm-hmm. 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 Yeah.
And so, people have been talking about this stuff forever, but they only get grounded when you can actually do some of the math that goes with it, or some of the gather enough data to either say yay or nay. But my impression with the $15 a wage is that too is very much dependent upon the context.
It does. It actually depends on the industry, and it highly depends on the geographic areas where you're looking at that. Yeah, because obviously a minimum wage of $15 is different in West Virginia versus California.
Right.
Yeah.
But I don't understand why people don't explain that or mention that, because it just comes out, it's a minimum wage always has this effect. And then I hear, something different. So for instance, in my understanding is Seattle has had a mandatory minimum wage for a long time. And same thing with, what is it? Connecticut, I guess it is, now has a mandatory minimum wage of something like $14 or $15. And those have all been successful, but that's because those are pretty wealthy places.
Yeah. So and so again, unintended consequences, or what we call in complex systems unpredictable emergence.
Well, of course, the system is designed to have unpredictable emergence.
That's right.
The other way of looking at learning is basically the reason the whole system is so incredibly has diversity popping up everywhere, and people come up with weird ideas, many of which are going to go nowhere.
Yeah.
Is for that kind of reason.
Right. I love it actually when I see in different fields of study how they rediscover the same concepts. They just call them differently. They just call them differently, but it's practically the same idea. So.
Well, no, that's my whole life experience. I spent a lot of time giving these talks to all these different fields, and in all over the world. And what I found was exactly what you just said, which is many fields have very similar concepts. They just call them by different names and have different sets of examples of, who studied it and who found what, and, that kind of stuff.
That's right. Yeah.
It's weird. Anyway. Okay, well, this has been wonderful. I think I'm going to pause now or stop.
Okay, sure.